Welcome to this lesson, to the story of electricity, one of the most powerful and world-changing journeys in human history. Over the next few moments, you're not just learning a subject, you're stepping into a legacy built by some of the greatest minds to ever live, pioneers like Faraday, Volta, and Franklin, who took something invisible, mysterious, and misunderstood, and turned it into the force that powers our entire world today. And everything you see around you, every light, every home, every piece of technology exists because of the discoveries you're about to explore. These men didn't just study electricity, they unlocked it. And today you are standing on their shoulders. Because this is more than a lesson. This is the story of how curiosity became power, how experiments became industries, and how a single spark became the modern world. And now it's your turn to understand it. So let's begin at the very beginning. To truly understand electricity, we must travel back thousands of years, to the ancient Greeks, where the first observations of this mysterious force were made. The ancient Greeks were the first to notice something strange. When amber, a fossilized tree resin, was used to make jewelry, it was rubbed with fur. It attracted lightweight objects like feathers and dust. They called this mysterious force electron, the Greek word for amber. For thousands of years, this curious effect remained little more than a curiosity. Fast forward nearly 2,000 years, and we arrive at a time when real scientific progress began to take shape, the 1700s. It is here that curiosity started to turn into structured investigation. But before we go any further, it's important to understand what life was like during this period. This was a world without electricity, a dim, slower-paced existence governed by daylight and candlelight, where even the greatest minds worked in near darkness. It was in this environment that the foundations of modern electrical science were first laid, making the discoveries that followed all the more remarkable. London streets were lit only by flickering candles and oil lamps, casting long shadows across narrow roads as horse-drawn carriages passed through the darkness. There were no electric lights, no televisions, no phones, no instant communication or modern conveniences. Life after sunset was limited, and much of the world faded into darkness. Even great minds like Isaac Newton worked by candlelight, studying, writing, and experimenting in conditions that were far removed from the bright, connected world we know today. It's hard not to wonder what great minds like Isaac Newton would think if they could see our world today, a world illuminated at the flick of a switch, powered by forces they were only just beginning to understand. The very principles they studied in quiet rooms and candlelight now drive cities, industries, and global networks. It was within this world that, by the 17th century, science was becoming more organized and structured. Isaac Newton played a key role in shaping this new era through his work with the Royal Society, a formal institution dedicated to understanding the natural world. One of those inspired by Newton's world was Francis Hawksby, a Fellow of the Royal Society, and one of the first to study static electricity systematically. Working closely with Newton, Hawksby became known for his meticulous experiments and careful observations of electrical phenomena in the early 1700s. Hawksby's most significant contribution was the invention of the Hawksby machine, a rotating glass globe that, when rubbed, generated static electricity and produced a visible glow. This was the first man-made electrical light, and it opened a new chapter in the understanding of electricity. What made it so remarkable was the implication that electricity and light were somehow connected, an insight that would eventually lead to the electric light bulb nearly 2 centuries later. Building on Hawksby's work, Stephen Gray was a scientist who took a keen interest in how electricity behaved. In the early 1700s, he began investigating whether the electrical charge generated by devices like the Hawksby machine could be moved from one place to another. Gray made a remarkable discovery. Electricity could be conducted, that is, transmitted along certain materials. He showed that a charge could travel along a damp string and that some materials were conductors while others were insulators. This was one of the most important discoveries in the history of electricity. Gray's distinction between conductors and insulators gave scientists a new framework. Electricity was not merely a property of objects, but something that could flow, be directed, and be controlled. With the understanding that electricity could flow and be controlled, the next challenge was finding a way to store it. In 1746, Peter van Musschenbroek at the University of Leiden invented the Leyden jar, a glass jar coated inside and outside with metal foil that could store an electrical charge. For the first time, electricity could be captured and released on demand. Scientists across Europe were amazed by its power. The Leyden jar was the world's first capacitor. Its invention caused a sensation. Reports spread of experimenters receiving powerful shocks, and for the first time, electricity felt tangible and real. News of the Leyden jar spread rapidly, inspiring bold new thinkers, none more daring than Benjamin Franklin. The American statesman and scientist had a bold theory that lightning was in fact electricity. In 1752, he famously flew a kite in a thunderstorm with a metal key attached to the string. When lightning struck nearby, a charge ran down the wet string to the key, proving that lightning and static electricity were the same phenomenon. Benjamin Franklin's experiments demonstrated that lightning is a form of electricity, a groundbreaking discovery at the time. By drawing electrical charge from storm clouds and comparing it to stored electricity in a Leyden jar, he showed that this powerful natural force could be understood and studied. This work led to the development of the lightning rod, which went on to protect buildings and save countless lives. Franklin proved that electricity was not just a laboratory curiosity, but a force of nature governed by laws that could be understood and harnessed, helping to usher in a new era of scientific and technological progress. Meanwhile, as global trade expanded in the mid to late 1700s, sailors returning from distant parts of the world brought with them not only spices and goods, but strange and fascinating creatures never before seen in Europe. Among these was the torpedo ray, a fish known for delivering sudden, powerful electric shocks. At the time, this ability was little more than a curiosity, something mysterious and unexplained. However, Henry Cavendish, a brilliant and inquisitive scientist, became deeply intrigued by this phenomenon. Henry Cavendish was one of the most brilliant and reclusive scientists of the 18th century. Though he published little, his private notebooks revealed extraordinary insights into electrical theory, including early calculations of electrical potential and resistance that were far ahead of their time. Henry Cavendish made a remarkable discovery through his study of the electric torpedo ray, a fish capable of producing powerful electrical shocks to stun its prey. By carefully dissecting and investigating this animal, Cavendish demonstrated that electricity was not confined to machines or atmospheric phenomena, but was also a natural force present within living organisms. This breakthrough opened the door to the study of bioelectricity, raising profound questions about the role of electricity in the human body, from the beating of the heart to the transmission of nerve signals and the movement of muscles. Cavendish's work sparked growing curiosity across Europe. If a living creature could generate electricity naturally, could it also be produced artificially? That question captivated Alessandro Volta in Italy. Driven by this curiosity, Volta began experimenting with different metals and conductive substances, setting him on a path that would lead to one of the most important inventions in history, the first electrical battery. Around 1800, Alessandro Volta made a remarkable observation that would change the course of science. He discovered that when two different metals were brought into contact, or even placed on his tongue, they produced a small but noticeable electrical sensation. This simple yet profound discovery revealed that electricity could be generated through the interaction of materials, rather than relying on natural phenomena like lightning or living creatures. It was this insight that set Volta on the path to creating the first continuous source of electrical current, an invention that would revolutionize the world. Building on this insight, Volta went on to construct the world's first true electrical battery, the voltaic pile. By carefully stacking alternating discs of zinc and copper, separated by layers of cloth soaked in brine, he created a device capable of producing a continuous and reliable flow of electrical current. For the first time in history, electricity was no longer a fleeting phenomenon. It could be generated on demand, controlled, and used, marking the beginning of practical electrical power. Volta's key insight lay in the relationship between different metals. He discovered that zinc, being more chemically reactive, releases electrons more readily than copper. When these two metals are connected in a circuit, electrons begin to flow from the zinc to the copper, and it is this movement of electrons that we define as electrical current. This breakthrough did not just advance electricity, it marked the birth of electrochemistry. For the first time, scientists could see a direct link between chemical reactions and electrical energy. Volta's pile was therefore not only a landmark invention in the electrical world, but a foundational moment in chemistry, revealing that chemical processes could generate, control, and sustain electrical power. This simple yet powerful principle underpins all modern electrical systems today, from batteries to large-scale power generation. Through his invention of the voltaic pile, Volta transformed electricity from a static curiosity into a dynamic and reliable form of power, laying the groundwork for every electrical system that powers the modern world today. But the voltaic pile's impact stretched far beyond power. It enabled the birth of electrochemistry. Scientists discovered that passing electrical current through liquids could split chemical compounds into their elements. This process, called electrolysis, led to the discovery and isolation of many new elements, including sodium, potassium, calcium, and chlorine. Electrolysis would go on to transform industry as well as science, used today to refine metals, produce aluminium, and even generate hydrogen fuel. In honor of his monumental contributions, the unit of electrical potential, the volt, was named after Alessandro Volta. His groundbreaking invention of the voltaic pile not only provided the first steady source of electrical current, but also inspired generations of scientists and engineers to explore and harness electricity. The principles he uncovered remain at the very core of modern electrical technology, forming the foundation of every battery used in the world today. Volta's invention marked a turning point. No longer limited to sparks or static charges, researchers could now experiment with sustained electrical currents in controlled environments. And among those inspired by this breakthrough was Humphrey Davy, a brilliant young scientist in Britain. With access to powerful voltaic piles, Davy began pushing electricity to its limits, using it not just to study electrical effects, but to unlock the very structure of matter itself, setting the stage for some of the most extraordinary discoveries in chemistry and electrical science. Humphrey Davy was a brilliant chemist working at the Royal Institution in London. Using an enormous voltaic pile, the most powerful electrical source available at the time, Davy conducted groundbreaking experiments that pushed electricity beyond anything previously imagined. In 1802, he achieved a remarkable breakthrough by passing electrical current between two carbon rods, creating the first electric arc light, an intensely bright, sustained source of illumination. It was unlike anything the world had ever seen, demonstrating the immense power of electricity and offering a glimpse into a future where light itself could be generated at will. Davy's spectacular demonstrations captured the imagination of audiences across Britain. Among those captivated was a young bookbinder named Michael Faraday, who attended the lectures with fascination, taking detailed notes and later sending them to Davy himself. Recognizing his talent and curiosity, Davy brought Faraday into the Royal Institution, a decision that would prove pivotal. For Faraday would go on to make some of the most important discoveries in the history of electricity, building upon the very foundations his mentor had helped to establish. In 1831, Michael Faraday made the discovery that changed the world: electromagnetic induction. He found that when a magnet is moved in and out of a coil of copper wire, it creates an electric current in the wire. This happens because the moving magnetic field pushes electrons through the conductor. Faraday's discovery proved that movement can be converted into electricity, forming the basic principle behind all modern generators. Faraday's next breakthrough was the first true demonstration of electricity being converted into motion, the foundation of the electric motor. By passing an electrical current through a wire placed within a magnetic field, he observed that the wire began to move. In his experiment, the current flowing through the conductor interacted with the magnetic field, creating a force that pushed the wire, causing it to rotate around the magnet. This simple but powerful principle showed for the first time that electrical energy could be turned into mechanical movement. Faraday had effectively created the world's first electric motor, a discovery that underpins everything from fans and drills to electric vehicles and industrial machinery today. In essence, magnets can move electrons. A changing magnetic field creates a force known as electromotive force that pushes electrons through a conductor. This insight unified electricity and magnetism into a single, interconnected phenomenon, laying the groundwork for all of modern electrical engineering. Yet even before Faraday's landmark discovery, another quiet breakthrough had taken place. Back in 1824, William Sturgeon made a pivotal contribution to electrical science with the invention of the electromagnet. By winding a coil of wire around an iron core and passing an electrical current through it, he demonstrated that electricity could generate strong and controllable magnetic fields. This breakthrough transformed magnetism from a fixed natural force into something that could be switched on, adjusted, and harnessed, laying the essential groundwork for technologies such as electric motors, relays, and transformers that power the modern world. With electricity now something that could be generated, stored, and controlled, inventors began looking beyond the laboratory. In the 1830s and 1840s, Samuel Morse harnessed electricity for communication, inventing the telegraph and Morse code. By sending pulses of electric current along a wire, messages could be transmitted across vast distances almost instantly. The first transatlantic telegraph cable connected America and Europe in 1858, shrinking the world forever. The telegraph was the internet of its age. For the first time, information could travel faster than any human or horse, and the world became electrically connected. But the story was far from over. Thomas Edison took electricity from the laboratory to everyday life. In 1879, after thousands of experiments, he successfully demonstrated a practical incandescent light bulb, a thin carbon filament that glowed for hours inside a vacuum glass globe. It was a moment that changed human civilization. In 1882, Edison opened the Pearl Street Station in New York City, the world's first commercial electrical power plant. Electricity flowed through underground cables to homes, offices, and businesses in Lower Manhattan. For the first time, a city was powered by electricity, and the modern age had truly begun. Edison hadn't just invented a light bulb, he had invented an entire system. The power station, the cables, the meters, the switches, and the sockets that would power the modern world. Yet Edison's system had a flaw that a rival inventor had already identified. Nikola Tesla, a visionary Serbian-American inventor, understood something Edison did not. Direct current, DC, was inefficient for transmitting power over long distances. Tesla championed alternating current, AC, which could be stepped up to high voltages for transmission and stepped down for safe home use, making long-distance power delivery practical and affordable. Alternating current, AC, is the backbone of modern electrical power systems, allowing energy to be generated, transmitted, and used efficiently over vast distances. Unlike direct current, AC continually changes direction, creating a revolving magnetic field within machines like generators and motors. This rotating field enables electrical energy to be converted into mechanical motion and back again, forming the foundation of power stations and industrial systems. From the generator to the transmission lines and into homes and workplaces, this image shows how alternating current, AC, is used to create movement in electrical machines like motors. When electricity flows through the coils, it creates a magnetic field that spins around, making the motor turn. The waves at the top show how the current changes direction in a smooth pattern, which helps the motor run steadily. In systems like three-phase power, this process is even smoother and more efficient, which is why it's used in factories and large equipment. This is how electrical energy is turned into movement to power real-world machines. Tesla's invention of the three-phase AC motor and his partnership with George Westinghouse made it possible to transmit electrical power across hundreds of miles with minimal loss. Today, the entire world runs on alternating current, and in that sense, Tesla won. From ancient amber to the global power grid, this is the story of electricity, a force that has transformed every aspect of human life. From the earliest observations of static charge in ancient Greece, through the curiosity of pioneers like Francis Hawksby, the brilliance of Faraday, and the revolutionary systems of Edison and Tesla, the story of electricity is one of persistence, discovery, and transformation. Over more than 2 centuries, what began as a scientific curiosity became the force that powers the modern world around us. Every light that switches on, every machine that runs, and every connection we make is built on the foundations laid by these innovators. Electricity is not just a subject you study. It is a legacy you now become part of. And as you step forward into your own journey, you are not just learning a trade. You are continuing one of the most powerful and remarkable stories ever told. So there you have it, the story of electricity, a journey that began thousands of years ago in ancient Greece and has evolved into the powerful force that drives our modern world today. Along the way, countless pioneers dedicated their lives to understanding it, working late into the night, experimenting, failing, discovering, and pushing the boundaries of what was possible. And now, that journey continues with you. As an electrical trainee, you are not just learning a trade, you are inheriting a legacy. The knowledge you are gaining has been built over generations, passed down from some of the greatest minds in history. You are, quite literally, standing on the shoulders of giants. So take pride in what you are learning, apply it, respect it, and build upon it. Because one day, you will be the one carrying this knowledge forward. The story of electricity is one of the greatest stories ever told, and now you become part of it.